So, as the title slide shows, today I would like to discuss with you some key concept and some key computational tools that allow us to study structural transitions. We will see what does it mean, structural transitions. I'm thinking to a broad range, actually, of processes, of phenomena. And we will see that two ingredients for this kind of studies are the order parameters and the kinetic rates. We will see that both of them actually are very important. And of course, there are specificity in each system we want to study, that's natural, but at the same time, fortunately, there are some very basic concepts that are universally valid and that allow to use really statistical mechanics, some basic theory to deal with very, very different phenomena. So I will try to show many examples in order to be interesting, so that my presentation will be interesting, and I will try to avoid a lot of formalism, of course. The point is not now to make a very detailed mathematical discussion. The point is really to convey some key concepts. So let me start from this slide where I wanted to point out, as you know very well, that today we have computational methods. I don't enter into details, but here we have a density functional theory, for example, in the picture of Walter Kohn. We have different computational methods that are very successful in describing a large range of physical or chemical properties of materials, let's say. For the moment, let's remain on solid materials. For example, here there are examples of graphite and diamond. And of course, a large part of our community is involved into creating and studying static models, meaning models where we carefully choose the atomic positions, and then we are interested in studying, for example, electronic properties, vibrational properties, and so on, without necessarily displacing the atoms, without necessarily studying the time evolution of the atoms. Now, this is, of course, a very important field, but I would argue that dynamics is even more fun. At least that's my personal viewpoint. And for dynamics, I mean here that, for instance, we can ask ourselves questions like, how do I pass in practice, in nature, in experiments, how do I pass from graphite to diamond, for example? Now, studying this kind of phenomena, this kind of transformations can be very, very challenging. So, of course, the model I show on the screen is very small, so you might argue that in nature, maybe, even if we find a beautiful mechanism in the simulation, you might argue that in nature, that's not exactly how it's going on. But the point is more general. Sometimes we can do small systems, sometimes we can do very large systems. Sometimes we have accurate forces, sometimes we have less accurate forces. But in any case, my main research interest and the interest of a large community is to study the dynamics, the evolution of the systems, and in particular, the transformation mechanism between different states. So this is the example where sp2 bonds start to disappear in favor of sp3 bonds. So we pass from 3 coordinated carbon atoms to 4 coordinated ones, and eventually we get to diamond. Now, in this slide, which is a bit complicated, many things, many pictures, but this is to give you a broad overview of the fact that despite the differences in all these systems, here you see different systems, you see chemical reactions, crystals, you see nanostructures, you see proteins, but from a theoretical viewpoint, actually, we can study really all of them in a unified way. Okay, so there is a way to study many different processes of this kind, many transformation processes in a way that is unified. And that's what I will try to convey today. Now, one might argue, why is it important to simulate transformation? So maybe I can find it interesting and funny, but is it really important? Is it really relevant in science or in computational science to study transformations? Well, there are different arguments. We can say that the transition pathways, so really the mechanism taken by systems to transform, are something that we will see is very evanescent, is very quick. The pathways are quick. So the transformations themselves, when we go from A to B and the structure changes, this is often fast. So this is something that is hard to catch in experiments. Now, it depends a lot, of course, on the system, but it could be something that takes between picoseconds to nanoseconds or hundreds of nanoseconds. depending on what you're studying, and sometimes it's even less. Sometimes it's tens of femtoseconds. So you might imagine that really having a clear picture of this in experiments, of these transition states and so on, is very difficult. Another reason why it's important to simulate transformations, it's a way to access some physical properties that are very important, like the free energy and the rates, the kinetics. We will see that in many cases, understanding an experiment or even predicting an experiment boils down to somehow reconstructing a free energy landscape or estimating kinetic rates. Then another possible reason today, which I think it's important, is that we have wonderful methods about in silico predictions. We can predict, for example, crystal structures. I think you had previous webinars organized by you, by people that really are pioneers in this field and that provided new methods like USPEC or ARSS or so on, where we are able to predict a lot of interesting structures. Maybe they have wonderful physical properties. Now, the point is, of course, we would like to synthesize them in the lab. It's very satisfactory to predict something, but we also would like to apply them in the real world. And then it's not so obvious how to pass from a structure that we predict to a recipe to synthesize it. Behind all these questions, there is a fundamental challenge, is understanding the interplay between thermodynamics and kinetics in determining the evolution of a system. As you know well, what we observe around us, from the trivial objects around us up to the most sophisticated technology, very rarely are systems in equilibrium. Very often what you observe are not the most stable phases, the most probable ones, but rather some unusual and improbable phases that are stabilized in a kinetic way. So this is really a central point. Okay, can we understand the interplay between thermodynamics and kinetics? Now, just show you, I would like to show you a couple of examples taken from our own lab. This is not work from me, but from my colleagues in Sorbonne in Paris, where, for example, in this article, they showed experimentally how to form and how to study amorphous ices. As you know, water has a very complex phase diagram. We have many crystalline phases, but also amorphous phases. And what is interesting to me, if you read some sections of this kind of papers, like the one I reproduce here, you realize how it's delicate and complicated to realize a given target structure in the lab. Maybe you have to compress to a very specific pressure and with a very specific temperature. Then you can change a little bit the parameters and the result changes. Then if you don't observe a certain protocol for the right amount of time, I don't know, 1 hour, you get a different result. So this is very, very delicate. When you read these things, you realize that metastability and kinetics play a central role. Once again, here it's the observations, the experiments are not dominated by the most stable states, but precisely the experimentalist tries to navigate among the different structures in a very non-trivial way, exploiting kinetics. So of course, the amorphous systems are an example, but also non-amorphous systems. This is another work from our lab, where they synthesized an open framework allotrope of silicon some years ago. So here again, in this case, you want to reach an ordered structure, but again, an unusual one because it's open framework, is not very compact. And then the way to do it is really complicated. Once again, if you read in the article, you find that something that looks really like a kitchen recipe. Okay, you have to start from some ingredients. You have to ground the mixture in a mortar for 1 hour. Then you have to pressurize to some pressure. Then you have to heat to some temperature for some time. This is clearly like a kitchen recipe, and this is the signature of kinetics. This is not something how to say that just leads us to the most probable state. This is a very delicate and precise procedure to get metastable states. Okay, so this is a bit an important point in what I will show next. From the point of view of theory, because this is experiment, but from the point of view of theory and simulations, are we able, or will we be soon able, to help our friends, our experimentalists, to synthesize materials and to find new recipes and so on? Or we have to rely on trial and error? That's a bit the question. Now, I try to point out here some key features, in my opinion, of these structural transitions we were speaking about, these transformations, okay? All these phenomena we discussed, they can be called rare events, or anyway, they can be characterized as rare events. And they have some common features. Here, the small animation shows the crystallization of liquid water, for example. Now, all these transformations, or at least a large class of this transformation, have this behavior, which is really an empirical observation. If you prepare the system in an initial metastable state A, for example, the liquid, this is the liquid below the melting point, and you let it evolve undisturbed, meaning you don't perturb it externally, you leave it at equilibrium, let's say. After a long time, it will spontaneously transform to B. So this is an empirical observation. It's a spontaneous transformation. We don't have to do anything special for it to occur. Then if we go a bit more into details, what we see is that the transition seems to happen at a random time. Now imagine to repeat many times the experiment. Well, this graph is a simulation, but it's the same idea. If you repeat many times the experiment, you really realize that the transition again happens at a random time, but it's not completely, how to say, undefined. There is a well-defined average, and there is a well-defined distribution, which is the exponential distribution. And this is a signature of a simple first-order kinetics. We could discuss about this, but now the point is not to enter into mathematical details. It's just to say that many phenomena belong to this class. And they have a very simple description in terms of first-order kinetics and an exponential time distribution. If we go a step further, we realize that a convenient way to study these systems is to introduce an order parameter. Now, some people call it order parameter, others call it collective variables, other reaction coordinate, but it's the same thing. It's a generalized coordinate, a generic coordinate. It can be complicated or simple. It can be a coordination number, can be the potential energy, can be the gyration radius of a protein. Many possibilities, infinite possibilities exist, but it's something that can describe the transition going from A to B, and out of which we can look at the process as a random walk on a free energy landscape. So imagine that as a function of the order parameter reaction coordinate, you can try to estimate or to draw a free energy landscape. We'll see better what it is. And the metastable states appear as minima, and the barrier appears as a barrier. there is a bump in the landscape, like in the plot. So from this viewpoint, once again, the transformation can be assimilated to a random walk on a landscape, and the fact that there is metastability, that there is this jump time exponentially distributed and so on, is the result of a high free energy barrier. High means much larger than the thermal energy, KBT. Now, it turns out, for obvious reasons, actually, that to simulate this kind of processes of phenomena is very hard. And the reason is simple, is because of the barrier, the transition time, the time of the jump, can be very long. And very easily, this time exceeds our computational capabilities. With ab initio molecular dynamics, density functional theory, today you can reach the nanoseconds quite easily for systems of hundreds of atoms. So if you have a force fields, you can go to larger systems and longer times, but in any case, you are limited to something like microseconds or perhaps milliseconds if we speak of atomistic simulations. If you do other things, it can be faster, but atomistic simulations where we have atoms, they have this feature. So here in this small blue table, I show that very easily, actually, you exceed by many orders of magnitude our computational capability. It's sufficient to have a barrier of 20 kcal per mole, which, if I'm not mistaken, is about 1 electron volt, to have already a time scale of a minute. And you just double the barrier, you pass from 1 minute to 1 billion years. So essentially, it's very easy. You just need to break a few chemical bonds, for example. It's very easy to have an extremely slow phenomenon. So forget about simulating directly with brute force this phenomenon. Now, what we do, what people do in this situation in the scientific community, well, they do many different things. There are many different algorithms. I try to schematize what is the typical, what are the key steps, the typical steps. So there are 3 steps, actually. Maybe people don't say it, but there are 3 steps conceptually. The first one, if we want to simulate a transition, we need to generate transition pathways. It might be trivial to say, but it's like this. You need, in a way or the other, there are many ways to do it. No one is perfect, but you need to have a guess, to have an initial pathway, to have something that brings you from A to B. I don't know, graphite to diamond. You need an algorithm that is able to bridge between the two. So you need a continuous transformation of your coordinates of your system. This is non-trivial, as I said, and you can find a mechanism that is wrong. Of course, you can find a mechanism that is irrelevant experimentally. So you don't just want to find one mechanism. You want to find the best or the realistic mechanisms, the most probable ones. So this, if you want, is a science of its own. It's a difficult topic. A second step, once you have transition pathways, a second step consists in trying to estimate free energy landscapes. Now, I didn't define it yet, but the free energy landscape is a very simple concept, actually. It's the same thing as the probability landscape. So if you choose, as I said before, an order parameter, we can call it Q. For graphite to diamond, you can think to the number of chemical bonds for each atom, the average number. So 3 is graphite and 4 is diamond, and something in between is the transition. So take your preferred order parameter. Imagine to make an infinite simulation. That's, for a moment, it's just a Gedanken experiment. And then make an histogram. This is the P of Q, is the probability histogram of your order parameter. That's the free energy landscape. You just do a transformation. You take the logarithm, essentially. But having the probability at equilibrium of the order parameter is the same as having the free energy landscape. It turns out that the free energy landscape is a bit more handy than the probability one, but it's the same thing. Mathematically, they have the same information. So we obtain, for example, this simple two-well picture that I showed before. Of course, it can be more complex, but that's the paradigm, the basic one. And how do you estimate this free energy landscape? As I said, either you do an infinite simulation, a very, very long simulation, but this you cannot, especially if the timescale, as I showed, is minutes or hours or so. So you need some tricks. There are algorithms that allow you to do free energy calculations without waiting forever, basically. But things get quickly complex. We will see some examples. So it's not something trivial. It's done by a large community today, but it's not yet maybe something that can be done with the left hand or with closed eyes. It's something really that demands expertise. Finally, there is a third step. Again, I put them in order because logically, if you don't have the pathways, it's difficult to do a free energy landscape. If you don't have the free energy landscape, it's difficult to have kinetic rates. So the third step is to compute kinetic rates. This is a crucial point. In many experiments, what really matters is the kinetics. Free energy landscapes are beautiful. Theoreticians like me, they like to draw them, to show them to colleagues, but actually what is really relevant often is the kinetics. How long it takes to observe this transition. If I rise the temperature, how much is faster, things like this. The kinetics makes the difference between something that can be applied in the real world and something that can never be applied. Okay, so it's important to control the kinetics. Now here the things are even more complex. There are a number of techniques, but really a zoo of different ways to estimate rates developed by different communities. This is a very tricky topic. Today still is not perfectly understood, I think. And doesn't even exist a very good reference to read about this. There are many fragmentary information. That's my point of view. But still, there is a lot of work that has been done. In the future, maybe we will have a more unified picture. We can do our best, in any case, to estimate accurate rates. Now, let's start from the problem of estimating free energy landscapes. As I said, we cannot generally rely on just brute force, infinite simulations. So what shall we do? There are a number of techniques. One of them is metadynamics, just quickly, because maybe many of you know it, but it's not the topic of today. But metadynamics is a smart idea developed by Alessandro Laio and Michele Parinello, where essentially you alter the local probability in the space of the reaction coordinate. So the local probability would be the exponential of the free energy. It's e to the minus beta f. So it's, again, due to the barriers, you are trapped basically in the local minima for a very long time. But imagine now to fill the local minima. Imagine to alter the landscape by adding yourself some repulsive bias. And this is the idea. You depose some bias, which is depicted in blue here. Initially, maybe you deposit here, then you jump out of the first minimum and so on. If you iteratively fill the landscape, fill the minimum with a bias, eventually you hope to flatten it. You flatten the barriers, you flatten the minima, everything becomes quite flat. And then if the landscape is flat, what you are left with is random walk. Random walk on a flat surface, it's not very complicated. If everything goes well, you have a system that diffuses very well between the reactants, the products, and so on. And then again, under some conditions, it's not trivial, under several conditions, you can extract not only the mechanism, but also the free energy landscapes. Now, all of this relies crucially on the reaction coordinate. I will tell you in a moment why. It's not as simple as it looks because we don't know usually what is the best reaction coordinate to use. A second way, an older one actually, is the umbrella sampling, where now the bias is static, is not time dependent. Essentially, you fix a parabola somewhere in your landscape. So look at the, I don't know, at the red parabola, for example. The red parabola is on top of a barrier, more or less. So imagine to run a simulation with the natural landscape, which is the black one. So your system will have tendency to fall from the barrier, but now you add the red bias, and then you can force your system, you can localize your system on the barrier, and you can collect as much statistics as you want. So this is a simple idea. You can have different biases, so different replicas to sample conveniently the whole landscape. And then you combine together the estimates, the probability estimates from the different windows, from the different biases, with some standard procedures. It's not super complicated. You can put together basically a landscape, unbiasing, removing the effect of the parabolas from your probability distribution. So this is just to mention a couple of techniques which are widespread. In both of them, but I would say in all the techniques where you sample a reaction coordinate and you apply maybe some bias to accelerate the sampling, in all these cases, it's very, very important the choice of the reaction coordinate or the order parameter. This is really the key ingredient. I would argue that many different methods are similar efficiency if you have a very good collective variable, and they all fail if you have a very bad collective variable. So it's crucial to have a good reaction coordinate, but the problem is, what does it mean good, or what does it mean optimal? This is a big, big problem, okay? Now, this is described often as a chicken and egg dilemma, meaning you would like to know very well all the possible structures, all the possible metastable states, the mechanism of the transition and so on, in order to define an optimal coordinate. Unfortunately, to reach to this level of knowledge, to explore very well the landscape and so on, you need an optimal coordinate. If you don't have it, as I said, you cannot rely on brute force. So this is really a non-trivial problem, and there is no well-defined solution. There is not a perfect or general solution. One can try different strategies, but it's really a profound problem in statistical mechanics, if you want. Now, one possible recipe we tried in the past, and we had quite some fun with it, is to try to define some general space of order parameters or reaction coordinates based on graph theory. So our task was to describe many possible transitions, nanostructures, solids, chemical reactions even. And we wanted to take inspiration from what is done in the theory of graphs that is applied, as you know, to Google, which is applied to networks of people, criminal networks, electric networks, brain networks, and so on. So there are very interesting applications and quite funny. What we try to do is quite simple in principle. So we take an object, we take an atomic system. Here you have 3 examples. And we look at it as an adjacency matrix. What does it mean? It means that we put on the rows and columns of the matrix the atoms, for example, the 60 atoms of carbon for the fullerene, and we draw a spot, like a red spot, if the atoms are in contact. You can define contact as you wish. It can be a covalent bond, it can be a hydrogen bond, it can be anything. In principle, it's proximity in space, and you are free to choose the range of the interaction if you want. So here it's just a geometric construction, okay? Maybe there is not even an interaction, I don't know. You define, again, contacts between atoms, or you can have contacts between amino acids, for example, as a matter of proximity in space, and you end up with matrices of this kind, these adjacency matrices. This is a bit the workhorse of graph theory. And you can hope to use this space of matrices as a convenient space to explore the transformations. This is the idea. The advantage is that it's very general. Here you have three very different systems: a nanostructure, a protein, and a liquid, and you can seamlessly look at them in the same way. Okay, you don't have to do anything special because they are different. Now, in practice, as I said, you define the distance based on the distance between atoms. You can define some sort of Fermi-Dirac or some sort of switching function, right, between 0 and 1, and you choose the range of the distances that you want to look at. Here, for example, between about 2 and 4 angstrom, there is the creation or the destruction of a contact, and you are free to choose. And then once you have a graph, you can try to start from it and basically define different order parameters. There is not a general recipe, I think. You can try different strategies, as I said. We tried several ones. Here are the three main ones that we tried. In some cases, you want to diagonalize the matrix, because then you can extract eigenvalues and eigenvectors, and they have a lot of very nice topological properties. You can think that the principal eigenvector is a little bit connected to the ground. It's like the ground state of the Hamiltonian, if you want to make an analogy. And this is similar to what is used by Google, for example, in the PageRank algorithm. In another case, we just take the full matrix of contacts and we sort it, and I will show you in a second. So it's a lot of information. We have many numbers. In other cases, we can build a sophisticated curvilinear coordinate that interpolates between different matrices. So again, it depends on the applications, but these kind of frameworks are pretty general still, because you can try really to apply to different systems without caring too much about the details. Now, this is just an example. I come back to the initial example. So here, it's an ab initio MD simulation where we have a density functional theory. I think it's PBE approximation, and we run at room temperature and some pressure that I don't remember, sorry. We run the simulation with a bias, so with metadynamics. If you don't put the bias, we can wait forever, but with the help of the metadynamics and of this topological coordinate, so in this case is the principal eigenvector of the adjacency matrix, we can see the transition to diamond in a matter of tens of picoseconds. So something we can simulate quite easily today. So maybe I will run it once again. What happens is interesting, even if this is a small model, it was just a small demonstration, but what you see is that the transition, since it's induced by the change of topology, our variables are controlling the topology of the atoms. So we are not pressing on the box. We are inducing a change in the connections. You see that the transformation begins at some well-precise place in the box, and then a bit with some hesitation in the beginning, and then it goes on and it propagates everywhere. And then the box itself adjusts because we have a barostat. So eventually you have something that, if the system was larger and if DFT is reliable, should be close to what could happen in an experiment. Okay. So this is the idea. This is the idea, and another way to play with this kind of systems, as I said, is to take the full adjacency matrix, which actually it's enough to take half of it because it's symmetric, and to put these numbers, which are real numbers between 0 and 1, in a vector. This is another way to play with these systems. If you have this huge vector, because if the system is large, this vector is huge. This vector represents the topology, the connections in the system. You can avoid the permutation invariance by sorting the components, for example, from the smallest to the largest. There are some techniques in descriptors for machine learning which are related to this today. But in our case, we did it really to explore the transition mechanisms. And then this huge vector is basically represents the topology, the structure of your system from the viewpoint of the connections. If you push the system to change this vector, you are pushing the system to change the topology, and maybe you make a transition from a liquid to a solid or between two solids. And we try to apply to different cases, and apparently it has a good resolving power. It's not perfect, you can find exceptions, but in many interesting cases, it's pretty useful, I would say, pretty effective. Then you can use this. So how to deal with these huge vectors? Well, you can put them into a framework of path collective variables. For example, this is is a flexible viewpoint where basically you want to go from A to B, and you define a b-dimensional space, one which is the progress from A to B, and one which is a sort of direction away from the path. So you have the possibility to have a simple paths, quite direct or complicated paths, and you can plot them in this b-dimensional space. The key ingredient, again, is a metric, is a distance that tells you if two structures are similar or not. As a metric, we use the comparison of these huge vectors that I showed before. And with that, you can have a simple functional form of two continuous variables. You can try to use them, as I said, for phase transition. So liquid to solid, solid to solid, and so on. Now, I don't enter into details. It's not I will be happy to answer questions, of course, but it's not the point now. This is an example of application where we did classical simulations this time, so 800 water molecules. We exploited the combination of metadynamics and umbrella sampling, and we demonstrated, I think for the first time, that it's possible to go from liquid to crystal, even from amorphous to crystal, from crystal to crystal, all with the same space of collective variables, the same space of order parameters. We don't have to, to change definition for each transition. It's quite general. And we can control really the transitions even in presence of large barriers. You can even have crystallization of liquid water above the melting point. It's already difficult below the melting point. Above the melting point, it means you go from favored liquid to unfavored crystal. But again, with the application of a bias, you can do it if the coordinate is good. So this is an example of application. Okay. Now, in the last minutes that remain, which probably is 10 minutes. Correct me, Gabriele, if I'm wrong. I would like to show you a second viewpoint, a slightly different viewpoint. So the same kind of problems. We want to study phase transitions and things like this. And now we look at it from a slightly different angle. Now, I reformulate a little bit the three tasks. You remember, I showed three tasks before. Now I changed them a little bit, but they are similar. So the first task is, again, we want to get realistic transition pathways, realistic transition mechanism. We want a connection between A and B. As we have seen, metadynamics is one way to get it. There are other ways. The second task is how to get an optimal order parameter. As I said before, this is a key point, because if we don't have a good order parameter or a good reaction coordinate, we will have a very hard time, for example, doing a free energy calculation, and then you can argue that even computing rates is very difficult. So this is something I didn't really discuss a lot. What is actually an optimal order parameter? I showed you that with some intuition and some applied mathematics, maybe one can find some nice definitions, but I didn't give you a rigorous definition, right? What is optimal in this context? So this we'll focus now. And then very much connected to this problem of finding the optimal order parameter, there is the problem of estimating accurate kinetic rates. I will come back to this. As I said, is a difficult topic, but we have to face it now. So the new approach that I will show you for this second final part of the talk is something where the points 2 and 3, so optimizing the order parameter and computing kinetic rates, this problem is solved by a joined, by unified approach, where we do both of them at the same time, point 2 and point 3, using stochastic models. I will show you what I mean with stochastic models. So it's quite different from the previous free energy calculation approaches. Actually, the objective for me, in any case originally, was, can we avoid expensive and cumbersome free energy calculation techniques? Be careful, when I say expensive, some people can say, well, if you have acceleration techniques, they're not expensive. You can have transitions and maybe free energies in a limited time. This is true, but usually you get to very good results that you publish after many trial and errors. You have to really find good, efficient reaction coordinates and efficient protocols. So maybe the final calculation is quite fast, but to get there, to get a satisfactory protocol, often is very, very time consuming. So today is not trivial. As I said, you need an expert often to do free energy calculation. So can we circumvent this problem? Now, just to reiterate that kinetic is difficult, this is a citation taken from an article in the literature where they try to do ice nucleation, so pure water, homogeneous nucleation, And they find, so using a lot of computer research and the best available techniques, they find an error of 11 orders of magnitude between the experimental and the theoretical rate. And this is something reasonable today, in the sense that today is so difficult to get a precise absolute estimate of rates. But you understand that this is not a satisfactory situation. We need to get to a precise rate estimation, as I said in the beginning, to help our colleagues doing experiments, doing synthesis. So why is it so challenging to estimate accurate rates? Well, there are two main problems, I think. One is that it's difficult to compute accurate barriers. So this concerns free energy calculations. And then we have a second problem that's very often is overlooked, which is that the barrier depends on the order parameter. So even if you compute in a perfect way the free energy barrier, maybe this barrier is not so useful to compute the rate because the order parameter you chose is not optimal. This is a subtle point. I will try to make it clear as much as I can. But again, it's not only about statistics. It's not only about doing enough sampling, efficient sampling. It's really about how we look at the problem, unfortunately. Let me show you this example. The problem in a mathematical sense is the following. We pass from the trajectory for n atoms. We have 3n Cartesian coordinates, and this can be a huge number. We want to pass from this to a single reaction coordinate, okay? A single order parameter q. This is called the projection. Basically, if you do this, you lose some information. This is intuitive. I mean, you cannot keep the same information after discarding all these degrees of freedom. What happens is depicted a little bit in this plot. This is just a schematic plot, but imagine to have a two-dimensional landscape with a double well, with two minima. You have coordinates x and y. Now imagine to turn sideways the landscape and to look, as in the right part of the slide, imagine to look at the landscape from the viewpoint of x. If you look from the viewpoint of x, basically you see very well the two minima, and you see very well a barrier in between. Now, if instead of x, you start to turn in the plane, in the xy plane, you start to turn to an angle of 30 degrees, 45 degrees, 60 degrees, and so on, what happens, of course, is that the two minima overlaps. They start overlapping, and then the barrier, the apparent barrier in between, decreases until it disappears. So this is a very simple sketch showing that the free energy landscape, and in particular the barrier, depends on the coordinate that we choose. If we look with some coordinates, we will have, for example, a large barrier. If we look with another coordinate, which is not very different perhaps, we have a very different barrier. This explains a little bit what I was saying. So we have to be very careful when we estimate free energy landscapes and barriers, and especially if we want to deduce the kinetics from it. We can get a very different kinetics if we have a high barrier or a low barrier, right? So this is a subtle but very important point. Now, I will skip some technical details. I will be very happy to answer if there are questions, but I don't think it's the time to enter into mathematical details. Let me just say that if you do the operation I said, so you take a complicated system of n atoms and you look at a single coordinate, and you can have whatever, different coordinates, of course, but you take a single one and you observe the time evolution in this viewpoint, you observe something like these graphs. These three graphs are trajectories initiated on the top of the barrier, on the transition state. In one case is ice nucleation, in the other is a isomerization of a small amino acid, in another one is a chemical reaction. What you observe are trajectories that relax up and down because these are relaxing in the two minima, A and B, from the top of the barrier. But the key point here is that the trajectories appear different. In different systems, in one system we can have a very smooth trajectory, which recalls a bit Newtonian dynamics, very smooth, like an oscillator. In another case, it can be very rough. It can recall a random walk, and we can have everything in between. So it turns out that it's very important, the resolution, the time resolution delta t that you use to look at the trajectory. If you print a snapshot every picosecond, every femtosecond, every nanosecond, you can get different roughness. Okay, let me say it like this, not to be technical. In practice, you can describe this kind of trajectories, projected trajectories, with a stochastic model. It can be a Langevin model, for example. And depending on the roughness, let's say like this, you can have different Langevin equations, okay? I will skip, as I said, unfortunately, some things. This is just to reiterate the importance of the variable. If you look at this graph, this is a very nice study done in the group of Utah Rogal, I think in New York. What they did is to study nucleation of nickel, and they consider two different order parameters. You see FCC, cluster size, or largest cluster size. So just to show that you get a very different barrier, depending on the parameter, the order parameter you use, and then you can infer a very different kinetics. So this is what I mean. This is a real problem. It's not a detail. It's a big problem. Now, what we propose, as I said, when you project from the molecular dynamics to one coordinate, you can get a Langevin equation. You have a ladder, you have a hierarchy of different stochastic models. Let's take the simplest one. The last one is the simplest one, is the so-called overdamped Langevin equation. Now, what we propose is the following. Basically, we start by generating trajectories, molecular dynamics that relaxes from the barrier top. This is typically done with transition path sampling. And this is our data set, our training set. So we have about 100 short simulations. We project on a chosen reaction coordinate Q, which is by no means perfect. It's our initial guess. We do some statistical inference. We deduce a Langevin model that optimally describes the dynamics along Q. And from this model, we ask this model, what is the free energy barrier and what are the kinetic rates? This can be done in a robust way, in a mathematical robust way. I can tell you if you are curious. And this, as an output, it gives you the rate. So as input, you give a coordinate, an input reaction coordinate that you chose. As output, you get a kinetic rate. Now, you can do iteratively this process, okay? You do just once the simulations in the first part, and then you try different coordinates, and each coordinate gives you a different rate. And you can iterate to improve the coordinate if you have an optimality criterion, right? If you have a sort of loss function or something that you have to minimize. What is this? Well, the mathematicians have demonstrated that, I think it was in the previous slide, mathematicians demonstrated that the loss function or the variational principle we are looking at, sorry, it's the first citation here, Zhang, Hartmann, Schutte, is on the rate. So the rate of the model should be minimized. One can show very solid mathematical arguments for which the minimal rate corresponds to the best order parameter Q. So minimizing the rate, you get the optimal order parameter. This is the idea. Not only that, but once you have the optimal order parameter, the rate, the corresponding rate, which is minimal, is the true rate. So at once, if we do this procedure that I show here, at once, we get two very difficult things. We get an optimal Q, an optimal coordinate, and the correct rate of the process. So this is the idea. This is the idea. And of course, we had to pass from mathematical theorem done by other people to applications. I will skip you the details. I can tell you if you are curious. We did it. We tried at least. And we started to study phase transitions, like in phase change materials, the transition from amorphous to crystalline. And we seem to obtain rates which are in agreement with brute force simulations. So this is encouraging. It's a collaboration. It's an ongoing collaboration with Julien Lam and Christophe Delago. We are trying to do it for protein-protein interaction. So we have two proteins assembling quickly, but then the time to disassemble is 1 day. And still, we can apply this inference technique with the short simulations, as I said, to infer the rate. This is much more difficult, but we are approaching. You see that if you go in this table from low to high, from the bottom to the top, basically the rate is decreasing, and we hope to reach very close to the experimental rate. So improving the variable means decreasing the rate until we should get the experimental, or at least the theoretical exact rate. This is a collaboration with Alessandro Barducci and Peter Bolaus. And with this, I finish. So this is the algorithm we proposed. You start from generating transition paths. As I said, there are efficient ways to do this. Emil Schult in our general transition path sampling, you can have efficient algorithms. You choose a large pool of trial coordinates. You make linear or non-linear combinations. You can use an autoencoder. You can use different approaches in principle. And then you do an optimization. So you iterate until minimizing the rate. This is an example for the interaction of carbon nanoparticles in water. You have that the rate is minimized. And when the rate is minimized, you end up with an optimal order parameter, an optimal reaction coordinate. And we got some evidence that this is true, at least in simple systems. Now, as I said, we are trying to apply to complex systems like nucleation of materials and protein-protein interaction. So I think it was already a lot of information. So I hope there was something interesting for you. I just end up with the acknowledgements. So of course, the people doing the hard work usually are the young people. So these are some of my collaborators that were really more or less involved in what I showed, and also some senior collaborators that I already mentioned, some of them. And I would like to thank you for attention, and I would be very happy to answer if there are questions. Thank you.